We can now go to the final topic of this long list of various items and deal and just give a short introduction to parallel computation. This is a huge topic that would take a whole course on its own. So what we deal with, what we mean for parallel computation? Well, as the name says, is we try to split our execution of our code instead of serial as it happens normally using one thread, one processor, in a set of threads or processors, or in a set of parallel computations. There are three ways here. I described two. There is another one, but actually Julia you can do, that is to parallelize at the level of the processor functionality. The two ones that I describe here are multithreading and multiprocess. Multithread has the advantage that is relatively computationally cheap. Why is this? Because it doesn't copy the memory. So under multithread you have one process where you have all your memory needed to run the program, and then you have different threads that run different operations, but where the memory is shared, and so it doesn't need to be copied. The disadvantage is that you can do this only within the number of cores of a single CPU. So you have a CPU with a process. A CPU has, for example, 8 cores. You can have 8 parallel threads, but because the memory is shared, it's also a bit dangerous because it requires attention to not overwriting the same memory or doing the operation of the memory at the order that is intended, and this is called data race problems, and so require careful planning. And also something specific of Julia, that we cannot add threads dynamically. We can only say start Julia with a number of certain number of threads, and we can do that using Julia with some options here in VS Code extension, or with the with this one. So we call Julia T4, and we started with 4 threads. But after we started Julia, we can no longer change. Multiprocess is a bit different. First, because it's not limited to the number of the threads, and it's not even when we deal with distributed computations, we are doing multiprocess, because we can also use CPUs that are hosted in other machines where we can connect through SSH, and so it's basically infinite the number of processes that we can work with. We can also add the processes from within the code, so it's not a problem in this case. We can just use add process and the number of processes to add, or we can also start Julia with P4 if you want already 4 processes. And the disadvantage, unfortunately, is that each process do some operations, but need to have available the memory that will use to do these computations. So each process needs to have its own memory, and this means that it's computationally expensive to make a new process, because you need to copy and assign this memory to the given process. Then if this process is on another machine, you have to account for the latency to reach this other machine. So you really need to balance the gain that you have in adding a process with the cost of setting this new process. So we try now to see some examples, some very basic example of these two modes, considering that if you are reading this document on GitHub pages, this document is compiled using GitHub Actions, where only one thread and one core really are available, even if you set more, and it ends up that you don't see improvement in the compiled documentation that is on the GitHub pages. But here you will see here now doing it. So here let's gonna create our inner function that I think is I don't know what it does. Okay, this is our inner function, and here we have our parent function, either using a single thread, or here you can see that to use multithreading is as simple as in the for loop to use these threads. So threads is the name of the standard library, and we use this threads macro here, and so this function inner just runs some computation, a sort of sum depending of one parameter x. So you return a scalar, get a scalar and return a scalar. And this both this single thread and this parent thread, they take a vector, so they take two arguments, x and how big is this the vector we want, and we fill with zeros, and then in this for loop it runs this inner function on each specific slot of our out vector. So notice here that this inner function is completely independent. So what I do here on the second element is completely independent to what I do on the third element, and so on. So it is trivially parallelizable, and this is why we can use this macro here, threads, because everything we do here relate only to one separate element of our vector. So we have our vector and we need to do y operations, each one on a different element of our vector. So let's gonna make 120, and let's gonna going to check that the two are the same, and we can see here that the order is preserved even if we are using threads. So we don't know in which one is written before the other, but the order in the vector is preserved. So I have 4 threads here, and the first one where I am operating is 1, it has ID 1. Let's going to benchmark the 2 implementations where I am, and I have 148 microseconds for the first one, and it should be much lower, okay, 50. So you can see here that even if I'm using 4 threads, the difference is not scalar with the number of threads, is not 1/4 of this 148, but it's still a quite good improvement. And let's now going to see how we can do something similar using multiple processes. And here, as I said, I have everything commented simply because because GitHub Actions seems to have some problems when I use distributed package, multiprocessed packages. This is something specific to GitHub Actions, so I cannot get this code running there, but we are going to do it here anyhow. So I'm using distributed, and as I said, I can add the processes dynamically, so I'm adding 3 processes, and I should get 3, 4, and 2, 3, and 4. The new ID, the ID of the process. So the first ID here is 1, and then I'm adding this the ID 2, ID 3, and the ID 4 that are considered the working processes. So here just some functions to work with these processes. So I can print the worked PID. I can remove one from the workers one ID. So here I'm removing the first one, and the first one is the PID number 2. So I have left the PID number 3 and number 4. So also this one I normally do not need it, since you need it, but anyhow it doesn't work. So this one is useless to do. So what I need to do if I want to run this my ID everywhere, I want to send it everywhere on all the process, this function here, println my ID, and I will get 4 and 3 from worker 3, from worker 4, printed everywhere. So here I did print the ID, and my ID is the function that return the ID, and I get it from the 2 different worker that I am left after I removed the one with ID 2. So what I can do with a process, I can do 2 things. I can run the typical things really is run heavy task in parallel. So again, let me using distributed, and here I'm creating a random function, a random matrix, 100 of so this is a vector of 100 random number from 1 to 45, and then I run a Fibonacci function in a recursive way that is known to be very long function. And the first things we need to do is, if you want to use this function, to call this function in different process, is we need to assign the function to the different process, and we do with the everywhere macro. So here we did it, and now we can use a function called pmap. P stands for parallel map. Map we already saw. The map apply a function, so apply all elements of a container, and they run this, call the function with the element of the container. So it's like you can x fib x is the same, and the parallel map, it applied this mapping, this calling this function with different elements, again in different processes. And here I have the output. So I want to benchmark, so let's gonna do it calling okay, here I am doing the same, so of course the result is the same. So here I should use the normal mapping. So here is the normal map in a serialized way, and this is the pmap in a multi-process way. And here I'm checking that the 2 are the same, and again also here the order of the result is preserved. So I don't know which process run the number 2 or the number 3 element of this array A, but I know that whoever process is doing that, then it is allocating back on the right element. So the results of this vector, given that A is the same, their 2 results are also the same. And when I do benchmark them, I can see that I have an improvement. I should have an improvement, but is not so big as in the other cases, as with threads. So I have 355 milliseconds for the single process, and when I'm using 2 workers, I have 200, so is well, actually it's not pretty bad. Is about half the time, because I'm using 2 processes to do the computations. You can see here something important. Here we have much more allocations, 158 kilobyte compared with just 800 bytes. This is because the memory, it has to be copied to the other to the 2 processes where do the computation. However, in this case, what is really matter is that this Fibonacci is really long, so it really irrelevant the time of this allocation compared with the cost of computing this Fibonacci function. This is really order of magnitude more important and dominate the benchmarking. This is why even if we are using processes, we have a pretty nice result by making this function using multiple, the computation of this function using multiple processes. So this is one way to use multiple processes using PMAP, where typically I have a long computation to do, and justify the fact that I'm using multiple processes. Another way is sometimes what we want to do is instead of having heavy operations where we are interested on the whole vector. So here we're interested as the whole result to not to a statistic or a summary of this one, but we are interested here to collect the results on the whole vector. Sometimes we want to aggregate the results in a single scalar, for example, out of a vector. And for doing that one, we have a nice macro that is distributed here, where we can specify which is the function to do the aggregations, and this work with a for block. So let me go again to uncomment this code here. Okay, so this is our single process where we have an operation relatively small, and here we do these relatively small operations where we over a for loop, but this for loop is the result of this for loop is used and by these functions to do the aggregation. So here we do the sum here inside the for loop, while here the sum result from the aggregation function given to the distributed macro. And here we run our benchmark. So here we have 11 microseconds, and here we have 6. So again, not pretty bad. The result is the same, and the improvement here is not again not so bad. You are very lucky with like in this case very often, and especially if you add more than 2 processes, you're starting to add 8-10 processes, you are not going to have an improvement of 8-10 times. But it's becoming less than proportional. So here is only the surface of what you can do with multi-processes and multi-threads, and you can read more about this parallelization and other kind of parallelization, like using, and you can use natively in Julia the GPUs or the TPUs, and this is very important for many machine learning algorithm, because they have to do matrix operation where the individual operation is very small, and for these kind of things GPUs are very efficient, and you can read more on this page of the documentation.